Thank you. Thanks for joining me at 9 a.m. for my lecture. So yesterday we talked about dark matter annihilation and decay and why particle theorists care about dark matter annihilation. Basically because it gives you a way in many models to produce the dark matter abundance correctly. And then we talked about the energy injection from dark matter annihilation into standard model particles and how that actually dumps a lot of energy into baryons. And so that leads to detectable signatures, for example, in the CMB. I was going to talk more in depth about what signatures you will see in the CMB, but after Julien's lectures, and there was so much detail in the lectures that I think a lot of what I'm going to say is kind of repetitive. So I think I'm going to change track a little bit, and tomorrow I'll tell you more about dark matter annihilation and heating of gas and how that can be detected from other cosmological probes. So the next thing that I was going to talk about was extra relativistic degrees of freedom. But before that, were there any questions from yesterday? Okay. So I left off yesterday by saying that, if we're thinking about extra relativistic degrees of freedom, there are two examples in the standard model. There are photons and neutrinos, right? And so it really is not, it wouldn't be surprising if in the dark sector, as part of dark matter or dark radiation, there are things that are ultralight, that are relativistic, either during BBN, during CMB, or even today, that are contributing to the energy density of the universe. And so let's think about how these things would work by considering what happens to the standard model neutrinos. Okay, and I'm just going to make a plot on the right here, which is scale factor and temperature. And I'm going to kind of detail what happens as a function of scale factor and also, yeah, maybe what I would write, I think A is a good choice. Yeah, all right. And so we know that standard model neutrinos at a time of BBN and at a time of CMB, they are relativistic. Furthermore, we know that at early enough times, they are in thermodynamic equilibrium. With the EM sector. And that's because of reactions that look like E nu to E nu, as well as nu bar to EE, and so on. Okay, so there are a lot of these reactions. They keep everything in thermodynamic equilibrium, so they at early enough times they have the same temperature as the rest of the standard model, and they have zero chemical potential, as does the rest of the standard model. So the energy density of neutrinos, of just one neutrino, would be 2 degrees of freedom, 2 spin states for the neutrino, and then integrating over just the density of states. So something like that. Okay, and you can work this out. And this gives you something that looks like 2 times 7 over 8, pi squared over 30, t to the 4. And let me just put a nu here. And then we said that 2 comes from spin degrees of freedom. There are 2 spin degrees of freedom per neutrino. 7/8 comes from the fact that it's a fermion. And then this is kind of like the unit of energy density, right? So for example, for photons, the energy density of photons is 2 times this number. For neutrinos, it's 2 times 7/8 times this number. All right? Then, we also said that at T T gamma equals T nu equals T decoupling, which is roughly 2 MeV, all of these reactions, the E nu, and the nu bar EE, all of their reaction rates drop below the Hubble rate. And at that point, we get decoupling of neutrinos from the EM sector. Okay? So if I go back to the temperature plot, initially, if I don't look above 100 MeV, where there are a lot of other things that are happening, such as QCD phase transition and so on, everything is kind of redshifting just as T gamma equals T nu equals to proportional to A inverse, until you hit some decoupling scale factor, A decoupling, which is roughly at 2 MeV. All right? And then after that, what's going to happen is that the neutrinos decouple, they free stream, and for the same reason that Julien mentioned above yesterday for the CMB, they stay in the Fermi-Dirac distribution, and they can be well described by equilibrium Fermi-Dirac distribution with T nu that just continues as also A inverse. Okay, so this is T nu continues to go as A inverse. All right. Okay, so that's nice. That's very simple. But now let's look at what's happening in the EM sector. Right? In the EM sector, at this point, what are the particles in the electromagnetic sector? Well, there are photons, obviously. It is 2 MeV, so electrons and positrons are relativistic, and they're populated with also energy density that goes as T to the 4. And so there are positrons, there are electrons. Okay? There are also protons, right? This is the protons are stable, and it's the lightest baryon that you have. So they're kind of just left over after QCD phase transition. And then there are also neutrons. And the reason why there are still neutrons, even though this neutrons are free to decay into protons, is because the splitting between these two is pretty small, and so they're able to interconvert into each other relatively quickly, and so they're able to stay in thermal equilibrium up to also roughly 2 MeV or so. We'll go into much more detail about this in the next lecture, which will be primarily on BBN. Okay. Now let's look at the mass of the electron. This is 0.me is equal to 0.511 MeV. And so at the time of decoupling, the electrons are still very relativistic, but they will soon transition into non-relativistic. And then the same thing happens as what we described with dark matter yesterday, right? So again, once T becomes less than or equal to ME, right? If the electrons are still in chemical equilibrium with the photons, they are in equilibrium with photons, and so there are processes like E plus E minus to gamma gamma, which are very efficient, right? And because of this, the number density of electrons will start becoming Boltzmann suppressed relative to, the number density of electrons will pick up this exponential factor, and again it will drop like a rock. And then at some point, unlike the dark matter case where we assume that, previously I said dark matter can self-annihilate, in this case, the annihilation is between particle and antiparticle. And the freeze out happens when you run out of E+, which remember, because of the baryonic asymmetry, you have fewer E pluses than E minuses. And so that's when this reaction turns off and you get a freeze out in the electron number density as well. Okay, so it's exactly the same, and you get a freeze out of electron density. Okay? Now, but if you think about it, in the process of this freeze out, all the E plus, E minus, they all get converted into photons. And these photons will free stream. They will all have at least 2 times, each of them will have at least energy given by the mass of the electron. And so that amount of, all of that energy will get dumped into the electromagnetic sector. And so the temperature of the electromagnetic sector at ME of roughly 0.511 MeV should show a little bit of heating, right? So what's going to happen is that the electromagnetic sector is going to start kind of heating up a little bit, and then at some point when the freeze out occurs, you're going to transition back to something that looks like this. Okay, and so at late times, again, you have T gamma proportional to A inverse, but then you have E plus E minus annihilation here. Okay, and neutrinos decoupled at 2 MeV. This happened primarily below 0.5 MeV. So the heating that went into the EM sector to first order doesn't go into the neutrinos, okay? So to first order, there's no heating of the neutrinos, although if you do this in detail, there is a slight correction, okay? So now let's try to figure out what happened here, okay? And it turns out that it's pretty easy to do in the end because we can use the fact that entropy is conserved. Okay, so you have an EM sector that's undergoing, these annihilations. Everything is in equilibrium, and the entropy of the electrons gets transferred to the photons. And so we can make use of the fact that all these processes are adiabatic, and so we have we can make use of conservation of entropy to compute something like T gamma over T nu at the end. Right? So once the freeze out is complete, this fraction, both of them are going to evolve as A inverse, and so this fraction is just going to be a constant. Okay? So let's compute the entropy density, SEM, at A decoupling. Open your textbook, your thermodynamics textbook, you will find that the entropy density of a fluid should be given by, the entropy density should be given by the energy density plus the pressure divided by its temperature. Okay? And if you look at this, right, this is proportional to T to the 4, also proportional to T to the 4 if everything is relativistic, right? Anything that's non-relativistic, let me just put a little parenthetical here. Non-relativistic DOF have negligible entropy. And so you can just consider just the relativistic entropy density, which is at decoupling, it would be photons and electrons. And so these both scale as T to the 4, and then you divide by the temperature, so it scales as T to the 3. And since I'm evaluating at A decoupling, this is just T decoupling, right? And so there are some prefactors that I don't care about, and I'm not going to bother you with them. But essentially, everything is just going to be proportional to T decoupling cubed. And then I'm just going to have to count the number of degrees of freedom, right? Because everything is just going to scale as T to the 4. So that just ends up coming out here, right? And so for photons, you have 2 spin degrees of freedom, so that's 2, right? As I mentioned up there. And then for fermions, you have electrons, positrons, right? Like I said, neutrons, protons don't matter. So electrons, positrons, there are a total of 4 degrees of spin degrees of freedom. They're fermions, and so I need a 7/8. Okay, and so this is the answer. All right, up to some prefactors. Okay. Now, after E plus E minus annihilation, okay, at some later time, at some scale factor A naught, doesn't matter when A naught is, as long as it's after E plus E minus annihilation. I can do the same calculation again, and that gives me SEM at A naught, and that's just going to be proportional to, in this case, because E plus E minus have already annihilated away, and the remnant is non-relativistic, you're just left with 2 degrees of freedom, and the temperature would be, T photon cubed at A naught. Okay? Now, in the standard model, after E plus E minus annihilates, the photon temperature just scales as A inverse forever until today, right? And so I can rewrite this. Well, okay, I don't actually have to do that, so forget about it. But what I did say made sense, which is that after E plus E minus annihilation, the temperature of the photon just scales as A inverse until today. Okay? And so by conservation of entropy, you can write the following, which is that 2 plus 4 times 7 over 8, T decoupling cubed, A decoupling cubed. Remember, this is just the entropy density, and so I have to multiply by the volume to get the entropy. This is going to be equal to T gamma at A naught cubed times A naught cubed. Okay? But then we also know that the neutrino temperature also scales as A inverse after T decoupling, after A decoupling. And so actually I can just replace this here with T neutrino at A naught cube, A naught cube. Right? Because the neutrino is just also redshifting as A inverse from T decoupling on all the way down to wherever A naught is. Okay? And so the A naught cube cancels, and you can work things out, and this just gives T nu cubed at A naught, but remember A naught is arbitrary, so as long as you're after E plus E minus annihilation, you get T naught cube, T nu cube is equal to 4 over 11's T gamma cube. Okay? All right, so based on an entropy conservation argument, I can already estimate what the neutrino temperature is. It's roughly 4 over 11's T gamma cube. Now, what goes wrong with this estimate? First of all, I already mentioned that I assume that when decoupling occurs, it's instantaneous, and it occurs only when electrons are relativistic. Neither of which are true, obviously, right? Decoupling takes a while. All of these reactions that I wrote down up there, right? They don't just suddenly shut off when they become unimportant. They're still active for a while. And so the decoupling is not instantaneous. And second of all, decoupling occurs at somewhere around 2 MeV. The mass of the electron is 0.5 MeV, so it's not really that far away. And so it really isn't true that E plus E minus annihilation starts entirely after the decoupling of the neutrinos. Okay, so when the decoupling is happening, some of the electrons are already, going a little bit non-relativistic. So if you include all of these effects, you get a correction to this. But before I explain the correction, because I know that rho nu, as I wrote up there, is proportional to T nu to the 4, right? This also means from here I get a relationship between the neutrino energy density and the photon energy density. And the way that we usually write it is what we do is we write things as rho r, which is the total radiation density, so total radiation density, okay? And this, in lambda CDM, this would include photons, and it would include neutrinos, the 3 neutrinos, okay? Minus rho gamma, okay, which again in lambda CDM, rho r minus rho gamma would leave just the 3 neutrinos. And we define something called N effective, which can be written as N effective times 7 over 8, 4 over 11 to the 4/3 rho gamma. Okay? So if this was exact, if this argument was exact, and you are in lambda CDM, cosmology, no other new particles, no other exotic, whatever, this would be 3 if T nu cube is equal to 4 over 11 T gamma cube. Okay, if. All right, so it's 3 if this was exactly correct. But like I said, it's not exactly correct. And if you do a very careful calculation, you find that N effective in lambda CDM is 3.043. All right, so do this carefully, you get a roughly 1% correction. All right. And there have been a lot of papers on this. At one point it was 046, 044, and now I think it's settled at 043. All right, so people really care about this number. Although observationally we're likely only ever gonna, well, at least in the near future, we're only gonna get up to this kind of precision. All right, any questions? Yeah. Yeah. Yeah, that's right. Yeah, very good. So it's something that I kind of glossed over, which is that if you think about what this reaction is, right, it should scale as like the rate, well, like dE minus dt should scale as Ne plus Ne minus times something, right? And because there's an asymmetry, Ne plus is not equal to Ne minus, it's a little bit smaller. And as you kind of deplete all of the electrons, this gets more and more important. And so unlike the dark matter case, the annihilation stops not when Ne minus squared is small, Ne minus squared sigma v is small, but when Ne plus Ne minus is small. And so it's an interesting question, which is that, because of the asymmetry that we have, the annihilation stops when there's like 1 electron every 10 to the 10 or 10 to the 9 photons. But if it was truly symmetric, it would stop at like 1 in 10 to the 20 instead. And so the asymmetry is actually really important at stopping this reaction. Okay? Any other questions about this stuff? Okay, good. Okay, so now what we're going to do is we're going to add new relativistic degrees of freedom. Okay? So new relativistic DOF. And the analogy is very, very similar, right? So now the only thing is that we allow the new relativistic degree of freedom to kind of decouple at whatever temperature it wants. Okay? And so if you think about it, maybe I shouldn't have drawn this with T gamma and T nu going as a to the minus 1. If you think about what's happening in the early universe, so similar to neutrinos, but decoupling can occur whenever. Okay, so one thing, yeah. I mean, before I jump into this, right? So what am I assuming about this new relativistic degree of freedom? I'm assuming that it was in thermal equilibrium with the standard model at early times. Okay, which doesn't have to be true. You could very well have relics that were never in thermal equilibrium with the standard model, but I'm just going to discuss the case where we assume that this new relativistic degree of freedom did come into thermal equilibrium with the standard model at some point. Okay? In that case, you get a situation which is very similar to neutrinos, but like I said, the decoupling can occur whenever it wants. Okay? Now let me draw this diagram. This temperature diagram is a function of A. How does it look like at really, really early times? So maybe at GeV, 10 GeV, and so on, right? So you think about what happens with E plus E minus. As you go up to higher and higher temperatures, the same thing happens with you also get annihilation of things like mu plus mu minus, things like pions, for example. You get pions having to decay into 2 photons, and so on and so forth. And so as you go back in time, the thermal bath is hotter and hotter. And when it's hot, it can produce all of these particles. And then when the temperature drops, all of these particles will freeze out in the same way as electrons. And so at very early times, you're going to see, okay, I'm drawing this really badly, but you're going to see little steps in the heating that takes it away from T goes as a to the minus 1. Okay, and then at the last step, there's neutrinos, and then there's the electron decoupling, which gives you T gamma. Okay, so what do you see here is that depending on when this decoupling occurs, right, the ratio of T, let me call it TNP, T new physics, compared to T new, is going to be smaller if the decoupling occurs earlier. Okay, and so the N effective that you get from T new physics depends very much on when the decoupling occurs. All right, so let's see how that works out. So we run through the same calculation again, right? So the same argument. Which is that at A decoupling, we have T new physics is equal to T new is equal to T gamma is equal to what I define as T decoupling. And at T decoupling, we have to count the number of degrees of freedom that contribute to the entropy, which we call G star S, at A decoupling and T decoupling cubed. Okay? This quantity here, which is the entropy density, should scale as, let's see, yeah, it's exactly the same as before. And so this quantity here is this thing, right? And then if we run through the same calculation as we did before, we would find that this would be equal to G star S at a new decoupling times the neutrino temperature at new decoupling cubed. Okay? And so when you follow the same logic, you'll find that, sorry, am I missing a factors of A? I think I am. So there is a, sorry, I made a mistake in my notes. So there's A decoupling cubed is equal to G star S, A new decoupling, T new at new decoupling cubed, A new decoupling cubed. Okay? And then using the same logic as before, you can see that T cubed of the new physics at new decoupling cubed is equal to the ratio of G star S at A new decoupling divided by G star S at A decoupling times T new at new decoupling cubed. All right? So this part here is exactly the same as the first line up there. And then I make the substitution that because after decoupling, T new physics just scales as A inverse, I can replace this with T new physics cubed at A new decoupling cubed, and then I divide by A new decoupling, and this is what I get. Okay? So what does this say? Just like in this case, right? I get a 4/11 here. Now instead of a 4/11, I get something that's more general, and it just depends on how many relativistic degrees of freedom there were at A decoupling compared to how many relativistic degrees of freedom there were at A new decoupling. Okay? Now again, you can repeat the same exercise. You can say, okay, well, the energy density of new physics is something like, depending on what this relativistic degree of freedom is, it has some number of spin degrees of freedom, G new physics, times pi square over 30, T to the 4, and then I have to multiply by 1 if it's bosonic, 7 over 8 if it's fermionic, right? And then I can make use of, sorry, there's an NP here. And then I can make use of this relationship to rewrite this in terms of T nu to the 4. And I can rewrite this in terms of the energy density of neutrinos. Okay, that's just some very simple math, and you can work it out yourself. But in the end, you get something like G new physics over 6 times G star S A new decoupling divided by G star S at A decoupling to the 4/3 times rho of all 3 neutrinos times 8/7 or 1 for bosonic and fermionic. Okay? And then from here, rho new physics, remember rho new physics is part of rho r minus rho gamma now, right? Because rho r minus rho gamma with the addition of this new relativistic degree of freedom includes both neutrinos and this degree of freedom. And so I can compute a change to the n effective, delta n effective, which again, it's just this, and then you relate it to 7 over 8's 4/11 4/3 of rho gamma. And this just ends up being something like n effective in the standard model divided by 6 times G new physics times this factor here, which is G star S A new decoupling divided by G star S at A decoupling to the 4/3 times 8 over 7 for bosons and 1 for fermions. Okay? And then this is the thing that you would try to look for in your cosmological probes. All right. Any questions about this? Okay, so the intuition from here, right, is that if you decouple earlier, you have a smaller temperature, you have a smaller energy density. The same thing is true here. If you decouple earlier, there are more degrees of freedom in the standard model plasma. And so this number is smaller, and then to the 4/3, and so this delta N effective goes down as your A decoupling gets smaller. In other words, you decouple earlier. Okay? So let me discuss the consequences of this. And so let's see. Yeah. Okay, so one thing that we know is that if we just assume the standard model, there are a finite number of particles, right? Within the standard model, there are 6 different quarks and 3 different well, 3 different leptons, 6 different leptons, neutrinos, and charged leptons, and so on. We have a full table of that, and we know that the highest mass particle is the top. With MT equal to roughly 173 GeV. Okay, so if we assume that a standard model is complete, which is somewhat of a big assumption, then once you go above this temperature of 173 GeV, you don't have any more particles to produce, and so essentially your G star S at temperatures greater than 173 GeV maxes out. And it maxes out at 106.75. Okay? So there's an upper bound to this number. There's an upper bound to this number. This number is known. It's just the number of degrees of freedom at neutrino decoupling, and I think it's including the neutrinos is something like 10.75. So we have G star S at T new decoupling is 10.75. Okay, and so if I choose the favorable situation, which is that GNP is 1, right? It's at least 1. And in that case, I'm forced to choose it to be bosonic, because if it's fermionic, it's spin half, it has at least 2 degrees of freedom. So that's the case where I have the smallest numbers for GNP and also including this factor. Then I can say that actually delta N effective that you would get from something that is thermal with the standard model, with no other particles except in the standard model, it has to be greater than or equal to N effective in the standard model divided by 6, and then it's like something like 10.75 over 106.75 to the 4/3. Okay, and this ends up being roughly 0.027. Okay? So if you can build an experiment that is sensitive to delta N effective of roughly 0.01, you have a hope of ruling out any possible relic that is relativistic during CMB and that is in thermal equilibrium in the standard model. assuming that the standard model is complete. Okay, if it's not complete, if there are like SUSY particles, like supersymmetric particles or whatever, then you will have more of these bumps at higher temperatures. And so if they decouple at higher temperatures, then this ratio can decrease some more. All right, but this is a very nice benchmark. And all of the CMB experiments like CMBS4, Planck, ACT, and so on use this as a nice benchmark for kind of searching for new physics with N effective. So there's a nice plot that is always shown, which is if I make a plot of T decoupling at MEV and delta N effective. Okay, you will find that the shape usually looks something like this. Okay, you get two bumps corresponding to neutrino decoupling, and here corresponding to QCD phase transition, which is roughly at around 100 MeV or so. This is around 2 MeV, as I said. Okay, and you will find that at some point it asymptotes to a constant value, and for scalar with 1 degree of freedom, this is 0.027. And any other choice you make, for example, fermions or scalars with 2 degrees of freedom and so on, they will all be a little bit higher. Okay? And then they will essentially phrase the delta N effective limits as being able to rule out something like this. Okay? And so if you look up the most recent ACT DR6 result, then you will find that some combination of Planck plus ACT has set a limit that is somewhere here. And so you can rule out any relic that came into thermal equilibrium below the QCD phase transition, which is roughly at around 100 MeV or so. All right, and if you're able to kind of push this down some more with more precise and effective measurements, then this line will come down, and the goal or one of the benchmarks that people have is to try to push this as close as possible to the scalar 1 degree of freedom example. All right. Any questions about this? Okay. So how do you look for delta N effective, right? I mean, this delta N effective is sort of the magic thing that that you want to look for, for this kind of stuff. I'm going to tell you how we're going to do it in BBN, which will be the focus of basically the rest of today's lecture as well as the later lecture. But then before I do that, I should also tell you something about how the CMB does it. I'm not sure if Julien is going to mention this, but I'll just go through it briefly, and then you'll probably hear more about it in Julien's lectures. But the idea is that what happens when you introduce new degrees of freedom that are relativistic during the CMB epoch, right? Like what happens? Well, oh, you will not do it? Okay, all right. But I didn't really prepare, so it's all of this is ad lib. So I'm just going to say some stuff, and hopefully it's correct. So delta N effective in CMB briefly. Okay, well, the first thing is, delta N effective more than 0 means that the radiation density goes up, right? And one of the things that the CMB is really good at measuring is the redshift at which matter radiation equality is achieved, right? And the reason for that is because the gravitational potential behaves really differently during radiation domination and matter domination, right? So if it enters the like if you have a mode for the gravitational potential that enters during radiation domination, then that mode decays really quickly. But if it enters during matter domination, then it doesn't decay. And so this difference between the behavior impacts the power spectrum very clearly. And so you essentially are able to see an enhancement of power um, um, at scales that come at scales that enter the horizon during radiation domination versus scales that do not. And so the CMB is very good at determining matter radiation equality. And so the matter density has to go up. Okay, to compensate for this. When you do your fits, if you add an effective, then this also tends to drive the matter density up. Another thing that happens is that because you have additional relativistic degrees of freedom, Hubble is a little bit higher, right? And so you essentially, the expansion rate is a little bit faster than you expected. And so the freeze out, kind of like when, like, you know, the amount of time needed to get to recombination decreases because of these extra degrees of freedom. Okay? And so this impacts the size of the sound horizon. A little bit. And it also gives less time for the photons to diffuse. And that's one of the most important effects, which is that there's less time for photons to diffuse. Okay, and so the picture that Julien drew, which is that, you know, photons are constantly kind of random walking as they are, you know, the universe is expanding. And if you give it less time, it has less time to random walk. And the thing that random walks do, you know, photon diffusion does, is that it kind of, you know, imagine if you have a region which is very overdense in the photons, and the photons are kind of allowed to random walk away and spread out. If you give them a lot of time, the like structures that are very peaked can end up getting spread out over a larger region. But if you give it less time, it doesn't have enough time to kind of spread out, right? And so this impacts, the main impact here is that it affects how much diffusion damping occurs. Okay? And so diffusion damping is this idea that if you allow diffusion to occur over a long time, all of the small scale structure that you had initially gets erased. Okay? And so some combination of all of these things, like it's not just this that's important, but also the fact that the matter density has to go up, and also because the sound horizon, you need to compensate for the change in the sound horizon, means that when you increase N effective, you tend to decrease, when you increase N effective and holding, you know, matter radiation equality fixed, plus sound horizon size fixed, you end up with less power at high L's. Okay, so it's terribly sketchy, but there are kind of like many effects here, and when you try to kind of hold matter radiation equality fixed and hold the sound horizon size fixed, which are the two most important things that a CMB fits to, you find that indeed this results in power being suppressed at high L. So if you look at the power spectrum, if you add an effective and you try to do a fit that kind of holds all of these things constant, it will push down power at high L. And so because of that, you're able to determine delta N effective. And so if I write down what the current determination is for N effective, which I have somewhere for CMB, it looks something like N effective is equal to 2.92 plus minus 0.18. This is Planck. But then also, it's kind of funny that like all of the experiments, the N effective value is a little bit scattered around. So I'll just write all of the determinations from the other experiments separately. This is ACT. And then SPT is 0.29 minus 0.33 SPT. Okay? So somewhat consistent with 3 at this point. All right? And this value here is the thing that's able to give you the constraint that I showed you, which is Planck plus ACT. So it's these two data sets combined. All right? Questions about, yeah? Theta S, yeah, sorry. I meant the angular size of sound horizon, because that's the thing that you see. I mean, in real space, that's the thing that you see. And so when you do the fits really want to just try to fix it to the value that you actually observe. And it's really complicated because, you know, the angular size of the sound horizon depends on the sound horizon, but then it also depends on the angular diameter distance. And so there are all these things that go in to kind of like adjust themselves. But at the end of the day, this is what happens. Okay? Questions before I move on? Okay. So the other way in which we can constrain delta N effective is through using BBN. And so for the rest of this lecture, and I guess also the next lecture, I'll discuss quite a bit about BBN and go through some of the details of how BBN works, what happens during BBN, how do we set limits using BBN, and so on. And then come back again to what happens when you have you know, extra degrees of freedom. Okay? Okay, so what is BBN? It's the process by which we get the lightest elements produced in the early universe, right? So again, think back to what's happening during the early universe at a temperature of roughly, you know, T of roughly MeV to keV. You've got nucleons, you've got neutrons and protons at these temperatures, which means that these nucleons are kind of like colliding with each other. And at these temperatures, it's enough to trigger nuclear reactions, right? As you see in the sun, or as we're trying to achieve in fusion reactions and fusion reactors and so on, right? And so you're going to get a bunch of nuclear reactions. And at the end of the day, as the universe starts off at very high temperatures and kind of cools all the way down to a keV, you're going to get all these nuclear reactions happening. And then at the end of the day, you're going to be left with a bunch of like heavy nuclei. Well, left with some nuclei like deuterium. Deuterium, which I'll call D. Also things like helium-3, helium-4, and along the way you will also produce tritium, lithium-7, and beryllium-7. So these are the main light elements that you'll be producing at this time. Of course, then there's also hydrogen, right? Okay. So what we want to do is we want to try to predict what the abundance of these elements are. This is tritium, which is 3H. This is 2H. Starting from like way above these temperatures where everything was just protons and neutrons and they were in equilibrium, which is kind of like a nice initial condition that we can start from. And then time evolved everything all the way till all of these nuclear reactions shut off, and then get a prediction of, we want to predict the abundances of these elements. Okay? And then what you can do is you can try to look for systems, and then we can look for systems that are primordial. And compare. Compare, abundance of D, of helium-4, and so on. Okay, so that's the goal. Okay, on the theory side, we want to be able to do a calculation that gives us the predicted abundances. And then on the observational side, we want to look for systems that we believe are primordial. And typically how people usually do that is they look for systems that are very low metallicity, so they don't have very heavy elements, because the heavy elements involve destroying these things in stars and supernovae and so on to go into heavier elements. Okay, and then they try to do a measurement of the abundance of deuterium, helium-4 on these systems, hope that it's primordial basically, and then compare it with what we compute. Okay, and so that's how this game is played. Why do we care? Well, any new physics active. Well, okay, we care about it for ΛCDM reasons as well, but from the new physics perspective, any new physics active between 10 MeV to keV can be probed. Okay, and then within ΛCDM cosmology, I should have done this the opposite way. I should talk about ΛCDM cosmology first before new physics. But within ΛCDM cosmology, this is a powerful probe of the baryon density, and then also the simplest extension to ΛCDM cosmology, which is delta N effective. All right. So what I'm going to do now is I'm going to step through the various things that happen, starting from high temperatures and then going down to keV temperatures. All right. So again, the original the thing that's going to happen at high temperatures is very similar to what I've already discussed in the case of electrons, right? So let me call this epochs BBN. Okay, at T much greater than MeV, But after, but less than 100 MeV, let's say, what do you have? You have photons, E plus, E minus, neutrons, and protons, and they're all in equilibrium. Okay, they're in thermal equilibrium. Photons E plus and E minus will scale as T to the 4, and these are all in chemical equilibrium. These two are in kinetic equilibrium, so they share the same temperature, but they're not in chemical. They have a chemical potential, and so you can't just get rid of. There's no way for you to just get rid of protons because protons carry baryon number. So these two are kind of different compared to these, but they all share a common temperature. Okay, now previously I looked at the electrons, so now let's look at the neutrons and protons. So how do they stay in equilibrium? Well, neutrons and protons can interconvert through, again, weak processes. Okay, so there are processes that look something like neutron plus a positron going to P plus nu E bar, for example. That's one. Then there's also neutron plus neutrino going to P plus E minus, and so on. And then there's also like neutrons. Neutrons are not stable, so they decay to proton plus electron plus nu E bar. Okay, so again, at early times, all of these processes are very, very fast, and so N and P are in thermodynamic equilibrium. Okay. And an important number to remember is what we call Q, which is the mass difference between neutrons and protons. Neutrons are a little bit heavier. You can see that neutrons can decay into protons. And this mass difference is 1.283 MeV. Okay, so that's a number that you should keep in mind. Okay, so at early times, easy enough. Everything was in thermal equilibrium. Neutrons and protons are in thermodynamic equilibrium, so they not only share the same temperature, but they can interconvert very rapidly with each other. And so that's a nice, simple starting point. And then the first thing that happens, which I've already discussed, is that at T of roughly 2 MeV, we get neutrino decoupling. Okay, so that we've already discussed. Then the next thing that happens is that it's the same story again. I've told this story many, many times, which is that once T starts dropping below Q, right? Again, neutrons and protons share a common temperature. They are in equilibrium. Once T drops to less than Q, the number density of neutrons picks up a Boltzmann suppression factor that goes as exponential of Q over T. Okay, so as temperature drops, this exponential factor becomes bigger and bigger. And maybe the thing that I should write is N over NP here. So relative to the proton, the neutron will start to decrease in number density because chemical equilibrium enforces this Boltzmann suppression. Okay? All right, and so the neutron number density starts dropping, right? But then also, the universe is expanding, and so all of these reactions, they're very similar in nature to the decoupling of neutrinos, right? So neutrinos has like nu bar to E plus E minus. Those are just weak processes as well. These are weak processes as well, so they have roughly, order of magnitude the same kind of reaction rates. So at around this temperature as well, these reactions are also becoming inefficient. And so at some point, you get neutron freeze out. When neutron to proton conversions become inefficient. Okay. You can do a calculation for when this happens. You can take these reaction rates, compute the reaction rates actually to first order, and then write down the Boltzmann equation, solve it, and ask when does freeze out occur. And the answer is that T freeze out. I'll spare you the details, but you can find some of the details in a textbook like Doddleson, for example. You'll find that the temperature of neutron freeze out is roughly 0.84 MeV. And so if I write down what the neutron to proton number density is at freeze out, this is roughly given by exponential of minus Q over TF, which is roughly 0.21. Okay? But it doesn't have this like devastating, crash to nothing as you saw for electrons, or as we expect in, for example, the WIMP freeze out and so on. And that's because this thing here, right, is roughly at the same order is at which these reactions are starting to become inefficient. And so once this happens, the exponential suppression starts. It starts, but then these become inefficient and then it just shuts off really, really quickly. And so you end up with an order 1 number. Okay? Another way that we usually write this is we define something called the number density of baryons. And this is just, nn plus np. And so in this case, nn over nb at freeze out is roughly 0.17. And this is just something that people usually say. All right? So that's good. Okay, so freeze out at this abundance, and then what happens, right? So if it was stable, the neutron number density would then redshift as just a to the minus 3, as we would expect, if it was stable. Okay, but free neutrons are not stable. They decay into protons, and so if you just kind of leave them alone for a while, they'll just decay entirely. All right, and you can ask, okay, what is the decay lifetime? And this you can measure in the lab, and tau n, well, depending on who you ask, is roughly 880 seconds. Okay, or about 15 minutes. All right, and so if you just let it freeze out and then nothing happens for 15 minutes, all the neutrons will disappear. Okay, and if that happened, then there will be zero initial abundance of neutrons primordially. You would just have protons. Okay, and I'm not an expert in this, but I think I'm not sure if that's bad for. Is it bad for star formation? Yeah, it should be, right? Because it's much harder to get fusion. Also for life, right? Can you get it? Can you get the high? Can you fuse it if it's just protons? I think not, right? Yeah, you need. Yeah. Okay. Okay. So obviously this didn't happen because there are neutrons everywhere. So um, what happened? Well, the interesting thing is that if neutrons get bound up in nuclei, then that's fine. You get stable nuclei. Okay, and so essentially within 15 minutes from the point where neutrons freeze out, which is at 0.84 MeV, you need to be able to producing start producing some kind of like heavy elements in order for it in order for you to have some number of neutrons left locked up in these nuclei ultimately. Okay, and thankfully that does happen, which is kind of strange. All right, so that's step 3. Step 4 was E plus E minus annihilation, which I also discussed. Okay, so this is a very busy time for everybody. Neutrinos freeze out, neutrons freeze out, and then electrons also freeze out, all at around the same time. Okay, and I think I've discussed this. All right. So, okay. Now let's figure out how much time neutrons floated around for. Okay, and that's the next thing that I'm going to discuss, and that's going to take quite a bit of time to explain. I have 15 minutes, so I will maybe get through half of this. But the next thing that happens is that the neutrons have to go somewhere, and so the first thing that it wants to do is it wants to look for, well, I mean, it doesn't want to, but it encounters a proton, and it can combine to form the simplest nucleus, which is deuterium, and then it emits a photon. Okay, so the free neutrons that are out there will try to encounter a proton, and then it will try to form deuterium, and that's great. Just for notational reasons, sometimes I will write this as n p bracket p gamma d, which is what people like to in the nuclear physics literature like to write. So the comma just separates the two sides of the reaction, and then typically they will put the kind of like the smaller constituents inside the brackets. And so this is a notation that people use very commonly. And so you say, great, this is fine. So why doesn't a neutron just immediately interact with a proton and go to deuterium? Well, if you look at the binding energy of deuterium, sorry. It's 2.22 MeV. And you say, well, okay, that's great. After freeze out, T is roughly 0.84 MeV. I'm below the binding energy, so I should be able to form a deuterium nucleus without any problems, right? But then the thing that you have to remember is that the backward reaction gamma plus D goes to N plus P, which breaks up deuterium. Right? Like I said, because BD is above the temperature of 0.84 MeV or so, you would expect that this is kind of inefficient. But don't forget that there are for every baryon, if I divide this by the number of photons, this is roughly 6 times 10 to minus 10. And so essentially for every deuterium that you form, there are something like 10 to the 10 photons out there. And so even though the temperature is at 0.84 MeV, at the high energy exponential tail of the distribution of the photons, there are still lots of photons that are able to break up deuterium at 2.22 MeV. Okay? And so after neutron freeze out, it's not possible to actually form deuterium in any significant abundance because most of them will actually get broken up by very high energy photons. Okay, so when do you have to wait until? You can do a more detailed estimate than this, but the naive thing that you would expect is that when kind of the number density of photons at the tail of the distribution is comparable to the number density of baryons. So in other words, you can only form deuterium when e to the BD over temperature of the photons is roughly 10 to minus 9. Okay, this is a very horrendous approximation, but it just gets you the physics. Okay, so pictorially, what am I doing? I'm just saying that I need to get to a point where in the distribution of photons, so this is the distribution of photons as a function of energy. This is the temperature. The peak is roughly at where the temperature is. I need to make sure that the binding energy is at some point BD such that the number of photons above the binding energy, which is just this tiny little wedge here, is roughly comparable to that of the baryon density. Okay, and this requires an exponential suppression of 10 to the 9. All right, and so you can ask, what is the photon? I mean, you know the binding energy, and so you can just immediately solve for T gamma, and that gives you something like let's see, what does it give you? It gives you something like TD is roughly 0.07 MeV. Okay, so what's happening here? Well, neutrons froze out at 0.84 MeV. It tries to form deuterium, but it's constantly getting broken up back into neutrons and protons. And really, you don't successfully form deuterium until it cools by 1 order of magnitude down to this temperature. And this is called the deuterium bottleneck. And you might think, yeah. Yeah. They do. They do, yeah. So now the next step is to figure out how much time actually elapsed. Yeah, and then we'll see that some of order 1 do decay, but not all of them. Okay? Yeah. So this is called the deuterium bottleneck, and you might be like, oh, this is very special in BBN, but actually it isn't. It happens for recombination as well, right? So if you think about recombination, you have a hydrogen atom with a binding energy of 13.6 EV. So you would have expected recombination to maybe happen at T of 13.6, but instead it happens at 0.25 EV or so. And it's the same reason. It's because you have to get down by an exponential suppression that's order 10 to the 9 before recombination can actually happen. All right? So it's actually very typical in freeze-out scenarios. Okay, so in this time between, so this is 6, between T of 0.84 MeV and T of 0.07 and TD TF of 0.84 MeV to TD of 0.07 MeV, you have neutrons decaying away into protons, and so you're going to lose some of the neutrons at this point. After this point, then all the neutrons make it into deuterium, and then subsequently they will go into the heavier elements. All right. So I have 5 minutes left, and the next calculation is pretty long. I'm just going to figure out like how much time actually elapses between these two, and then figure out what that means for the neutron to baryon number density um, going forward. Okay, so I think maybe I'll stop here and take questions. So it's a good point to stop. Okay, yeah. Oh, okay. I was not going to mention it at all. I was not going to mention lithium at all in this um, uh, lecture. So let me give you the background. Like I said, what did I say? I said that the name of the game is to get the theoretical prediction right and then compare it with data, right? And so the theoretical prediction involves doing these calculations. So this just tells you what the neutron number density is, and then figuring out how it goes from deuterium all the way to things like lithium-7, for example. And then there's the observational side. So there's long been a tension between the predicted value of lithium-7 and the observed value. And the predicted value is higher than the observed value. And the way that people used to do this observation is that they would look for, again, very old, low metallicity stars and try to determine the abundance of lithium-7 within these stars. And they find that there's some discrepancy between the theoretical prediction and the measurement. So let me just draw this. So this is lithium-7. This is theory. And this is experiment. This is measurement. And I definitely know this on a regular day, but now I'm blanking on how many sigma the discrepancy is. If anyone knows, can you just tell me? Is it 2 sigma? I want to say 2 sigma, but I'm not sure. 3 sigma? Okay. 3 sigma. Okay. This is interesting, right? But only if you can trust either the theory or the measurement. On the theory side, the uncertainties are quite big, but there isn't anything obvious that makes it that wrong. But then on the measurement side, you start to worry, right? Because you are doing a measurement of lithium abundance in stars, and then you worry that when you do the measurement, you are hoping that when the lithium-7 is formed in the star, it doesn't get convected down into the core of the star where it gets destroyed and things like that. And so there are clever ways to kind of assess whether the measurement, whether lithium-7 is being destroyed in the star or not. I don't remember the original argument, which is something called the speed plateau, off the top of my head. But the most recent study, which I do remember, is what they do is they look at lithium-6 in stars. So lithium-6 is formed by cosmic rays hitting the surface of the star and causing the formation of lithium-6. And you can try to see, do you observe lithium-6 in stars at the level that you expect from cosmic rays? If you do, then the lithium-6 that's formed on the surface kind of stays there and it doesn't get convected down and it doesn't get destroyed. If you don't, then possibly some of it is getting destroyed in the core. And that latest study shows that it's possible that lithium-6 is being destroyed in the core, and so the abundance can drop from the theory to measurement. That was lithium-6, and the argument is that lithium-7 should be similar. And so that gives you some evidence that stars can actually destroy lithium-7. And so doing the measurement in old stars is not good enough because you're not accounting for the destruction after the primordial abundance. So that was the status 2 years ago. But last year, something interesting happened, which is that Another group did a measurement of lithium-7 abundance in a cloud that is in the Large Magellanic Cloud, a cloud of gas, and that's not in a star, but they were able to find a low metallicity cloud in the LMC that they could then measure the lithium-7 abundance. And there they also found a 2 to 3 sigma deficit. And that's not a star, so you can't destroy it, right? So then the question is this thing real? I don't know because I'm not an expert on the measurement side. But I think right now it's in a confusing stage. I think for a while it was like, no, this is not a real problem. But now, like with the latest result, I'm a little bit confused by it. Yeah, it was like last year. Yeah. So if you're interested, it's a measurement done by Hauk et al. I'm not sure if he's the first author. I apologize to the first author, but I know Hauk, and he and some other collaborators did a measurement of lithium-7 in the LMC, and they do see a discrepancy as well. So I think that's interesting. Yeah. That, sorry, and then but then you go like, okay, how do I reconcile this? Well, what I need to do is I need to just destroy lithium-7 after it's produced primordially, and so you can try to put new physics to do that. But then the issue is if this happens, you probably destroy other things as well. And so it's also kind of hard to get this to work out, even with new physics. And so it's a little bit of a it's got a little bit of a Hubble tension kind of flavor, but on a much smaller scale. Yeah. 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 Yeah, sorry, I wasn't very clear about this. So usually what people do is they do lambda CDM, which has 6 parameters, and then they do extensions. So this is under the assumption that it's lambda CDM plus one more parameter, which is n effective. So you let n effective float, and then they do the fit and they find this. Yeah, you can do like n effective plus like a couple other things, and that kind of shifts all of these things around. So it really depends on what you assume. But this, I'm just reporting this model. Yeah. 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 Yeah, so like after like all, so one of the ways that you can do it, for example, is like after all the reactions are done, you introduce some like out of equilibrium decay to kind of smash the lithium up. But then you also smash other things. Yeah, and so it's a bit, I mean, the law that I've heard is that it's difficult to do this. I haven't really thought about this myself, but yeah. Yeah. Only lithophilic. Yeah. Actually, I think Seth Corrin has a paper about this. Yeah, so you're not even like, yeah, you're right. Yeah. All right, thanks. Yeah.